Hello, and welcome to Analyzing Arguments. I'm going to make that go away. Oh, how nice. All right. Welcome to Analyzing Arguments. There we go. I finally got my controls under wrapped, but I don't know how to stop the recording now. So let's just go with it. Today we're going to talk about analyzing arguments. And there are two types of arguments to look at. There's inductive, where you have specific premises that lead to a general conclusion. For example, bluebirds can fly is a premise. Hummingbirds can fly is a premise. Cardinals can fly. You getting a theme here? Our conclusion, all birds fly. It's not true, but it's an inductive type of argument. We go from the specific, bluebirds, hummingbirds, cardinals, to the general. All right, so think of it as a specific goes general. So we start here and we say something larger. A deductive argument, on the other hand, starts with general premises and goes to a specific conclusion. So we have a bunch of this general stuff filtered us down to just this one idea that has to be true. So, premise, all doctors are intelligent. I knew I should have rated to right. Dr. Jones is a doctor is a premise. Conclusion, Dr. Jones must be intelligent, right? General, all doctors are intelligent. General, Dr. Jones is a doctor. Very specific, Dr. Jones is intelligent. So from general, it filters it down, leads it down to a specific argument. All right, now we have to evaluate both inductive and deductive arguments, right? It's just because it's a type of argument, and it's not like a screaming match. It's just a way of discussing things. An argument is setting up your side. So in inductive arguments, it's making statements really is all it is. Talking is our arguments. An inductive argument does not provide it, does not prove its conclusion is true. So it's evaluated based on its strength. An argument is strong if a compelling case is made for its conclusion. But an argument is weak if the conclusion is not well supported by its premises. Okay? So let's look at an example of a hit movie. A movie director tells her producer, the guy with the money, not to worry, her film will be a hit. As evidence, she cites the following facts. She's hired big stars for the lead roles. She has a great advertising campaign planned, and it's a sequel to her last hit movie. Explain why this argument is inductive and evaluate its strength. I just want to say, a sequel to the last hit movie, Godfather 2. Oh, wait, Die Hard 2. Oh, wait. There's a whole bunch of movies that explains why this is not very strong argument. Why? But why is it inductive? Each of the three pieces of evidence is a specific characteristic of her movie, and the director uses these facts to support the conclusion, right? I got big names. I got this advertising campaign. My first one was a hit. But the conclusion is more general than the premises, right? The premises are this happened, this happened, this happened. I think probably in the future this is going to happen. But it's relatively weak because even, as I mentioned, a couple of them, the best planned movies can flop. All right. When it comes to a deductive argument, remember, deductive, you're deducing. You're deducting, so you're going from the general to a smaller thing. You're deducting information, getting it down to the basics. We apply two criteria to evaluate. First, the argument is valid if its conclusion follows necessarily from its premises, regardless of the truth of the premises or conclusions. All right, regardless of the truth of the premises or conclusions. It's valid if the conclusion has to follow from the premise, no matter what those premises or conclusion are. Now, the argument is sound if it is valid and the premises are true. Okay, so it's a good structure of an argument with nonsense. Well, it's valid and unsound. But if it's a good structure, the conclusion follows from the premises and all the premises are true, then it's both valid and sound. All right, so it cannot be sound if it is not also valid. Now, you can look at this table a little bit more in the book. I cannot direct you to the exact page, but it's in section 1D, so you can find it there. I'm not going to go over it, but take a screenshot if you need to look at it longer, or hit pause. All right, we're going to use a Venn diagram to test the validity of a deductive argument. So first step, we're going to draw a Venn diagram that represents all the information contained in the premises. Then we'll check to see whether the Venn diagram confirms the conclusion. If it does, then the argument is valid. Remember, we're using deductive, so we're looking at valid and then sound. If the diagram does not confirm the conclusion, the argument is not valid. So let's look. Evaluate the validity and soundness of the following argument. All fish live in water. So we're going to go with things that live in water, and we're going to put all fish in here. Right? The premise, all fish live in water. All tells us it's a subset. So we have fish as a subset of things that live in water. Whales are not fish. Right? Whales are definitely not fish. So it's outside of the circle for fish. But is it inside the blue circle? Is it outside the blue circle? We don't know. And when we don't know, we put an X on the border. But it has to be outside the fish circle. It doesn't tell us where it should be, so we just have to put it on the border. Whales do not live in the water. So we have a premise, and a conclusion. Whales do not live in the water. The conclusion, whales do not live in the water, would require an X here. Right? That's what the conclusion would require. But the X from the premises, right, it's on the border. And since we don't have this situation, the premises do not support the conclusion, it is not valid. And therefore it's not sound either. Let's see what they tell us here. Oh, they didn't tell us there. So yeah, it doesn't support it. Because we don't know exactly in the blue, out of the blue, where does it go? We put it on the border, and that tells us there's something fishy. Sorry. Basic forms of conditional deductive arguments. This class is the best mine for puns, and I can't resist. I know most people call them dad jokes now. I'm not a dad. I'm a grandma, but I still find puns hilarious. Okay, so we have 4 basic conditional arguments of the deductive type. There's affirming the hypothesis, saying P is true, affirming the conclusion, saying Q is true, denying the hypothesis, saying P is not true, or denying the conclusion, Q is not true. Now, hypothesis can also be replaced with the term antecedent, as conclusion can be replaced with consequent. I'm a fan of these words. I don't do antecedent and consequent very often, just so you know. I'll only use those when I have to. So our structure is always if P then Q, if P then Q. If P is true, Q is true, we're saying yes, P is true, then Q has to be true, and this is a valid argument. If P then Q, and we know Q is true, that does not indicate that P is necessarily true. That's an invalid statement. There may be other things that happen that make Q true also. If P then Q, excuse me, I'm saying P is not true, then Q is not true, and that's also invalid. P is not true, but again, there could be some other way to make Q true that is not P. Also, denying the conclusion. So the first and the last have the same validity. If P then Q, Q is not true. Well, if Q is not true, then P could not have happened. That is valid. If P is true, Q is true. Has to happen because of the conditional statement. If P then Q and Q is not true, then P is not true either. These are valid both because they have the same type of reason for validity. Let's look at affirming the hypothesis of valid statement. Consider the following argument. If a person lives in Chicago, then the person likes windy days. Carlos lives in Chicago. Our conclusion? Carlos likes windy days. Let's take a look. We're going to use a Venn diagram to show that the argument concerning Carlos and Chicago is valid. If the first premise is P, then Q, in which P, a person lives in Chicago, and Q, the person likes windy days. If a person lives in Chicago, then they like windy days tells us that P circle is inside the Q circle, right, or sets. I know that Carlos lives in Chicago, so our X goes in lives in Chicago. And so Carlos likes windy days? Yes, most likely Carlos likes windy days. The X of Carlos living in Chicago is also an X in Carlos likes windy days. So everything's good. But yep, I just covered that part. I put an X in the P circle to show that P is true for Carlos. Because the X is also in the Q circle, Q must also be true for him. I just didn't realize they did it in 2 steps instead of 1. The conclusion states that Q is true for Carlos. Carlos, he likes windy days, which means that if the argument is valid, we expect to see the X that represents Carlos inside the Q circle. The X is indeed within the Q circle, so the argument is valid. I don't know that it's very sound, though. I don't think the premise, if you live in Chicago, you like windy days. Maybe you just like Chicago and deal with the wind. Kind of like for us in Las Cruces. I love Las Cruces, but that doesn't mean I like windy days. See Spring, if you need an example. All right. Affirming the conclusion, invalid. Use a Venn diagram to test the validity of the following argument. If an employee is regularly late, then the employee will be fired. Drew was fired. Conclusion, Drew must have been regularly late. So what we're saying is we're affirming Q, right? So we're affirming the consequent from that table. Now we're going to start with a Venn diagram for if P then Q, which means the P circle is inside the Q circle. All right, so let's draw a little one here. We have our rectangle of all things. We have P, an employee is regularly late, and Q, great circle, the employee will be fired, right? If P, then Q. So P has to be inside of Q. Look at that. If I would have been patient, you wouldn't have had to see an ugly one. Look at that. Same exact circle, right? But what do we have? We know that Drew was fired. So inside the blue circle. But is it inside the pink or just the blue? But we don't know, right? So it's on the border. It's definitely inside the blue. So it's not on the border here and it's not in the tan background. Beige, whatever you want to call that. But we don't know if Drew was regularly late or not. So the second premise asserts that Q is true for the person named Drew. We draw, I want to just point this out right here. Sorry, that's eraser. That's not very helpful. I think something weird's going on in the writing. It's not a problem, whatever. If it's true for the person named Drew, excuse me, he was fired, we draw an X to represent Drew and place it inside the Q circle, but is it bordered or not? Well, that's all I'm saying. From one slide to the next, look, things change, whatever. The conclusion states that P is true for Drew. She was regularly late. Therefore, if the conclusion is supported by the premises, the diagram should have the X that represents Drew inside the P circle, but it doesn't. It's on the border, so the argument is invalid. All right. More Venn diagrams. Validity of the following argument. If you liked the book, then you loved the movie. You did not like the book. So this is deny the hypothesis. Conclusion, you will not love the movie. We start with a Venn diagram. For if P, then Q. With P, you like the book, and Q, you'll love the movie. All right, so you like the book, you'll love the movie. The second premise asserts that P is false for you. So put an X outside of the P circle. But is it here or is it here? Right? We don't know. So we place it on the border of the circle for Q. The conclusion states that Q is false for you. You will not love the movie. So if the argument is valid, we expect the X to be outside of the Q circle. But it's not. So the argument is invalid. In other words, it's possible that you will still love the movie even though you didn't like the book, and that happens for me quite frequently. Like one, but not the other. And this is exactly what our Venn diagram look like. So I like it. I like it. We did well. Good job. And denying the conclusion. So use Venn diagram to test validity of the following argument. A narcotic is habit forming. Aspirin is not habit forming. Conclusion: aspirin is not a narcotic. All right, so this is not the conclusion. We start by rephrasing the first premise in the standard condition by writing, if a substance is a narcotic, then it is habit forming. All right, if a narcotic, then it is habit forming. It's easier to set up our logic if we write it in the standard if-then format. But not all words and sentences in life doesn't come at us in nice mathematical setup. Sometimes we have to rewrite it and we have to make sure it's the same thing. So if we set the first premise up with if a substance is a narcotic, then it is habit forming. P, a substance is a narcotic. Q, the substance is habit forming. And we could draw the Venn diagram. The second premise asserts that Q is false for aspirin. It's not habit forming. We therefore place an X representing aspirin outside of the Q circle, right? What do we have? We have P. We have Q. And we have our box. Habit forming, narcotics, habit forming, aspirin is not habit forming. The argument is valid, right? That's exactly what we expect. It's outside of our aspirin is not a narcotic. And here we see the Venn diagram that I just showed you in a very, very sloppy manner. All right. Now, sometimes life isn't just if this happens, then that. Sometimes it's, well, this has to happen, so that's set up, so this occurs, and then we could go get dinner, right? It's just one thing after another that everything kind of has to set up. This is the common type of deductive argument as well. It involves a chain of 3 or more conditionals. So if we have 2 premises, if P then Q, and if Q then R, we'll set up a natural conclusion if P then R. And this is a transitory process. Transitive property that you'll find in mathematics. This particular chain of conditions is valid. If P implies Q and Q implies R, it must be true that P implies R. Let's look at an example. If elected to the school board, Maria Lopez will force the school district to raise academic standards, which will benefit my children's education. Therefore, my children will benefit if Maria Lopez is elected. It's election season. We're going to be hearing a lot of this. So we could break this argument down and rephrase it as a chain of conditionals. The first premise, if Maria Lopez is elected to the school board, then the school district will raise academic standards. Okay. If the school district raises academic standards, then my children will benefit. Conclusion. If Maria Lopez is elected to the school board, then my children will benefit. P to Q, Q to R, tells me P to R works. In this form, the conditional propositions form a clear chain from P equals Maria Lopez is elected, to Q the district will raise academic standards, to R my children will benefit. Therefore, this argument is valid. All right. Now, math is all about proof, and this is, it goes all the way back to the Greeks in, let's call it 700 BC, because I can't really remember. It's actually BCE. Proofs have long been a part of mathematics, and a mathematical proof is a deductive argument that demonstrates the truth of a certain claim or theorem. A theorem is considered proven if it is supported by a valid and sound proof. Although mathematical proofs use deduction, the theorems are often discovered by induction. So we'll use induction to try to figure out what this property is, and then we'll have to prove it using deduction. Here's an example. For all numbers a and b, a times b equals b times a. Well, is that true? I don't know. Let's check. 7 times 6, that's 42, and 6 times 7, also 42. The other ones, they work out, right? If I want to multiply decimals, if I want to multiply negative values, if I want to multiply fractions, it works when I switch things around. This is actually called the commutative property. The three test cases are each somewhat different, fractions, decimals, negative numbers, but the rule works. It offers a strong inductive argument in favor of the rule. We haven't proved that A times B equals B times A, but we have good reason to believe it's true. Our belief would be strengthened by an additional test that confirms the rule is true without specifics. We would test that using just variables. That's higher math. We don't need to get into that now. I appreciate you listening to this. Let me know if you have any questions on the homework.